This now we recorded. And right. Oh, nice. Okay, so let me remind you what we did last time. So basically, or maybe before I start, that's just a short logistical comment. So you've seen that we put homework 4 online. So just a reminder, it's due, we said June 11, which is, a week from now, roughly. So, but if you have any questions, just, ping us. But hopefully, it should be sort of, when next word that it's a guided sort of solution. So you have to sort of fill in the steps. So I think it should be sort of, doable. But yeah, if you have questions, just, ask us on Salos or Piazza or something. Okay, so what did we do last time? So basically what we did was we started discussing sort of, MC algorithms. And in particular, so the one MC algorithm, so MC stands for Markov chain Monte Carlo algorithms, and the high level idea that you want to sample an object from some complicated sort of objects. And the way we do this is first we find some initial objects, and then we sort of make local changes to get to a new object. And then if you do it enough time, then this converges to a uniform object, in our sort of allowed objects. And this could be like, we've seen an example of a spanning tree, but other examples we're going to see are clicks or colorings of a graph or other examples. And the main challenge here was sort of analyzing sort of the mixing time of this random walk. So let me just remind you, spend the next 5 minutes reminding you of what we've done last time, and then we will see how to make progress beyond that. So the example we saw was this sort of spanning trees. So the setup was with a graph G, which is VE, and let's call this curly T be the set of all spanning trees T in G. So to have a spanning tree, we'll assume this graph is connected. Otherwise, there's no spanning trees here. And again, the goal here was to sample a near uniform T in this curly T, set of all spanning trees. And what was the algorithm? So the algorithm was very, very simple. So step 0 maybe was so find some T, let's say T0. It is to start with some arbitrary fixed, spanning tree, and then repeat some number of times the following thing. It's called an update process. So we want to update Ti to Ti plus 1. So given Ti, we generate the next one as follows. So A, so we're going to choose the random edge E in Ti and remove it. And then we're going to complete it back to a spanning tree by adding another random edge that is valid. So choose a random edge E prime, which is not in, I guess, Ti minus E, and such that Ti minus E union E prime is a spanning tree. And then add it. So yeah, and just write as succinctly as follows. So Ti plus 1, take Ti, we remove a random edge for it, and then we add another random edge to it, such that, such that this new graph is also a spanning tree. So we just keep repeating this process. So every time we have a spanning tree, and every time there's some randomness in this process, right? There's two steps where there is randomness. Which edge we remove is random, completely uniform, and then also which edge we add is uniform among all the edges that we can add to the spanning tree. And then the main question, so we saw this general fact that said that it says after infinite time, so we get uniform T and T, but of course we don't want to run infinite time. So the real question was, well, how many steps should we do it until this converges to be very close? And then to the uniform thing, and the theorem we saw that, let me see here, so that the mixing time was, I think it was something that I don't know. So the mixing time, which is the number of steps to get epsilon close to uniform, is something like order, I think it will be n squared log 1 over epsilon, something like that. Maybe there's some log factors here, but polynomial time. And the way we proved this was actually by connecting this to walks on high dimensional expanders. So what was the idea? So the idea was we can define complex. So let's say we have n nodes. So each spanning tree has n minus 1 edges in it. So the complex is going to be n minus 1 dimensional. So we're going to set x0 to be all the edges. So that's going to be the basic elements that we could add. And the top level is going to be basically all the spanning trees. And then we complete it down by containment. And then what we saw is that this algorithm, this mix is exactly the same as the lower walk on X. So this process of taking a tree, removing a random edge, and then adding another random edge so that I get a spanning tree is exactly the same as starting with the top face of this complex, moving randomly to a node at level n minus 2, and then moving randomly again to a node at level n minus 1 again. So this was the way we define it. This was you take dn, so dn minus 1, un minus 2. So n minus 1, because this complex has n minus 1 levels. So now we basically show that, well, to analyze this algorithm, what we really need to understand is this complex. And then we saw two theorems. So theorem 1, we saw that so this complex X is a 0 local spectral expander. So we sort of analyzed this complex, and we used Oppenheim theorem to argue, to show that it's enough to show that the top level, like level max minus 2, is a 0 local spectral expander, and then all the other levels below it are connected. And we sort of prove this sort of combinatorially based on the structure of spanning trees. So that was part 1. And then part 2 said that any d-dimension, let's say for any, let's write this way. So let X be a d-dimensional zero local spectral expander, then the second eigenvalue of this walk that we care about, I guess this is going to be, now if it's d-dimensional, it's going to be more generally the ud minus 1 is at most 1 minus 1 over d. Which proves this, so this shows, so a corollary of that, well, that's, the mixing time is order of d, which is 1 minus lambda 2 times, log the size of the top level of the complex over epsilon. Basically, after every d steps, you get constant mixing, and then it log the number of nodes in the top level divided by epsilon. So this was a generic approach that we saw last time. And this applies not just for the spanning tree complex, but for any complex that is a zero local spectral expander. And so the crucial property here that we used last time was this zero local spectral expansion. Okay. So this is a recap of what we've seen last time. So any questions on that before I move to the next material? Okay. So what we want to do today is start asking, well, what if the complex is not a zero local spectral expander? I mean, zero local spectral expander is a very strong property. It's satisfied by this sort of spanning tree complex. It's also satisfied by other complexes, which are a basis of matroids, but basically that's it. So people have proven that the only complexes which are zero local spectral expanders are basically basis of matroids. But there are many questions that we want to study which are not basis of matroids. So some examples of things that we might be interested in are the following. So we're interested in many complexes, in many, let's say, MC algorithms that correspond to complexes. So for example, we care maybe about colorings. So this coloring, so you have a graph and you want to color its node with a certain number of colors, I don't know, 3 colors, so that the graph is going to be, this will be a valid coloring. Now this is not, if you take this complex, it will not be a zero local spectral expander. Also, maybe another one here is clicks. I want to sample clicks in a graph of a certain size. And sort of, at least to me, the reason these are not zero local spectral expanders is because we don't typically also even hope to find a color in a graph or a click in a graph. These are NP-hard problems. So we need to assume something about the structure of the graph so that it's even possible to find the initial point. But given that, it's not clear why we should hope that this would be this zero local spectral expander. What if it's a half? What if it's 2/3? I mean, what we've seen so far doesn't allow us to analyze this. So what we're going to start doing today is start developing techniques that would allow us to move beyond zero local spectral expanders towards more general expanders. And the concrete question I want to tell you about now is about sampling independent sets. Of course, clicks and independent sets are the same question. So just for concreteness, let's look at independent sets. So what we want to prove to you is the following theorem that says, and let G VE be a graph with maximum degree delta. And then I want to find independent sets in this graph. So I'm sure you all know that if you give you a graph with maximum degree delta, then it's very easy to find an independent set of size n over delta plus 1. Basically, just greedily choose a node and remove all its neighbors. And what we will show is that if you slightly choose smaller k, you can even find a random k click in this graph. So then, okay, let me also denote something just for completeness. Okay, let M be the unnormalized adjacency matrix G. Okay, now let's take the value K to be at most N over delta plus lambda 1 of M. That's going to be the value of K for which we can actually get mixing. So I just want to, before I'll keep writing, I just want to make sort of, maybe just write the theorem, then I'll tell you a few comments on that. Then the MC algorithm that samples K independent set, so independent set with K nodes, mixes fast, mixes. Let me just write mixes fast for now, then we will see the actual bounds later. Mixes fast. So in time, polynomial in all the parameters we care about, so n of 1 over epsilon. So I just want to, first of all, two things. First of all, what is this natural MC algorithm? So that's one question. And the other question is, why do we get this sort of weird bound here? So let's first do that. So what is this MC algorithm? So again, it's going to be, you know, this sort of, you start with an arbitrary solution, then you keep changing one at a time. So, you know, so 0 is that you start with some, let's call this click, I don't know, C. Oh, let's call this maybe S, which is a K independent set. So just find one arbitrarily. And again, you can find it because, so it's easy to find because K is less than N over delta plus 1. So even if you just do it greedily, like you choose an arbitrary node, add it, remove all its neighbors, and keep doing, you're going to get this bound, N over delta plus 1. So it's easy to find. Also notice that lambda 1M is something that's going to be between 1 and delta. So okay. And then again, what's going to be the random step? So the random step is going to be, you know, remove node, add node. So given an independent set of size K, you choose one of its K nodes randomly and remove it. And then you ask, well, let's take of all the nodes I could add, it's going to keep this in an independent set, add one of them randomly. Okay, that's it. It's a very, very simple process. And again, the main question here is the mixing time. So now, okay, now the question is, how can we analyze this complex? Okay, but the question is clear. So I mean, I think at this point it should be pretty straightforward how we start with such an MC algorithm and we view it as a complex, right? So now, and the only thing that's not clear, of course, here is for what values, or in this case of K, of parameters, we can actually analyze this complex and prove it's, you know, a good expander. So what should be the complex here? Who can tell me? So what complex corresponds to this this MC algorithm? I want to define a complex so that the lower walk in this complex would exactly be this random step in this algorithm. So what should be, so anybody, what should be the faces of this complex? Okay, what should be the dimension of this complex?
Maybe just to clarify, we're sampling fixed size. So you pick it, it's not for all k less than this parameter, you fix a k, and we want to sample independent sets of that exact size k.
Oh yeah, thank you, yes. Yeah, I didn't say that, yeah. So we fix a k and we work only for this specific k. Thank you.
So that means that we have a k-dimensional complex?
True, yes, it's going to be k-dimensional. What's going to be the basic elements of this complex? I guess it should be x1, so the way we write it, so x1. What should be the basic elements of this complex?
Well, we're sampling the, is it the nodes of the graph?
Yes, exactly. So it's nodes, right? So an independent set is a collection of nodes. And what's the top level faces here? So what sets of size k do we want to include?
The cliques.
Well,
Or
independent
yeah. Yeah.
It's going to be all this S, where S is a subset of V, S is size k, and S is an independent set, right? So that's the collection of all possible independent. And then you can see what's the lower walk of this complex. So you start with a k phase, so it's a set of size k, which is independent set. You move to level k minus 1 by removing one of the k nodes randomly. So now you have an independence of size k minus 1. And then you move up again, which is in a random node, you can add back to it and still get an independent set. Right? So then the low, so this MC algorithm, so the MC update step is exactly the same as the lower walk index. Okay, so all that we did is sort of translated sort of terminology. We haven't really proven anything yet. We just sort of changed notation to this language that we sort of use to work with complexes. So we encoded the constraints or the objects we are trying to find or to sample by the structure of the complex on which we're operating. Right, so before, with spanning trees, the top level faces were all spanning trees. So walks on this complex corresponding to moving from one spanning tree to another spanning tree. Now the complex has all independent sets as its top face. So again, going from one top face to another top face is a walk from independent set of size k to another independent set of size k. So what I want to emphasize here is that really all of the information on the question we're trying to study comes when we define the complex. So the complex encodes the type of objects we are trying to understand. So any questions on that before we move to analyzing it?
I guess maybe this question is like better for after we do the analysis, but like, will this work for like clique as well, or is there something special about independent set?
Okay, so yeah, cliques and independent sets are the same, just the assumption is going to be different, right? So you want to work in a regime where it's easy to find independent sets, so the degree should be small. So similarly for cliques, we want to move in a regime where it's easy to find cliques, so the degree is very high. So in this case, the minimal degree is going to be maybe n minus 1 minus delta or something like that. Okay. So okay, so now what can we say about this complex? So here's a fact that we're not going to prove. Let's write this. So here's going to be a fact that we're not going to prove. And we're going to say that, so first of all, two things. First of all, for every I at most k minus 2, and for every tau in xi, this complex x tau is connected. And 2 is going to be that, for every tau in xk minus 2, x tau is a 1 over k spectral, local spectral, or let's say spectral expander. This is a graph now. Spectral expander. Okay, so we're at a position to apply Oppenheim theorem. But let's see what would happen. So to see what happens, so this is a top level phase. So the point that we can apply the trickle down theorem. But here's going to be a problem. The top level is going to be a really good expander, like 1 over k. But as we keep trickling down the complex, the expansion is going to get worse and worse. So just to analyze this, let's see. So let's look at the following definition. So here's the definition. Let's define, so for I at most k minus 2, define gamma I to be the maximum lambda 2 of x tau over all tau in xi. So all the I phases, right? So within at every level, we don't like before we talked about local spectral expander, we went over all possible phases in the complex and asked which one is the worst expander. And if they all were great expanders, we were happy. We call this a local spectral expander. But now we're taking a more refined look. I'm saying, well, let's look in each level individually and see how good of an expander it is on this specific level. And we'll see why this is useful in a second. Okay, but for now, let's take my word on it that that's going to be useful for us. And let's see what do we get. 1 second. So let's do a calculation. So what do we know? So because of this fact 2, we know that gamma k minus 2 is 1 over k, right? So the top level is a really good expander. But then we can apply by the trickling down theorem, if I is less than k minus 2, then we get some bound on gamma I that's going to be worse, right? So gamma I is going to be what? It's going to be most. Let's just find a calculation here so I don't make a mistake. So it's going to be, well, the max one, so 1 over k, divided by 1 minus k minus I minus 2, 1 over k. So this is a trickling down theorem. So we get worse, so it's not, so it's 1 over k, so it becomes slightly bigger and bigger. And you do the calculation, you get this becomes 1 over I plus 2. Okay? So what's the problem here? So what do we have? So the top level is a really good expander. Right? We get top level 1 over k. But the bottom level is not, right? The bottom level is not. So gamma 0 is a half. So if we take all the levels together, then we get that this is really a half local spectral expander, right? This is how we define local spectral expansion. We took the max over all possible levels, all possible phases in them. So this is not a very good local spectral expander, but it's only becoming bad at the bottom levels. The top levels are also nice and fine. Just the bottom level is problematic for us. And the question is, can we prove that the lower walk mixes when most gamma I are good? And by good, I mean much less than 1. So what we want to say is, can we get a bound that depends not on the maximal gamma I for all of them, like we saw before? If they're all almost 0, we're fine. This mixes fast. But what if most of them are very close to 0, but a few of them are bad? And turn out the answer is yes, you can do that. So here's going to be the theorem that we're going to prove today by Alev-Lau. And it's really going to be, I mean, what we saw last time, we saw this simplified version of the theorem where all the gamma i's are 0. But the full-blown theory we're going to prove today is going to handle the case where most of the gamma i's are close to 0, but a few of them can be bad. And it says the following thing. So here's a theorem. It says, so let X be a D-dimensional complex. And again, we define gamma I to be the maximum lambda 2 X tau over all tau in Xi. So we're asking all the faces in level I should be somewhat good, or as good as they can, one-sided expanders. Notice, by the way, this is a notion of one-sided expansion, which turns out to be the useful notion in looking on sampling or mixing type results. Then you can prove a bound on the second eigenvalue. Then let's say it's for every k between 0 and d. We're going to analyze a lower walk at level k, right? So this is a lower walk at level k. So we go down and we go up. Now trivially it's most 1, but if most of the gamma i's are close to 0, we can actually put this as a bound away from 1. And concretely the bound they prove is the following: it's most 1 minus 1 over k, the product of I going from 0 to k minus 2, 1 minus gamma I. Okay, so this is the theory. And we're going to prove the theorem today. And the proof is going to be a modification of the theorem we saw for the gamma equal to 0 case. So it's going to be a refinement of the same proof, which is why we decided to show it to you in steps. So first we saw the simplified version for the 0 local spectral expansion. And today we're going to see the full-blown proof for this case. Now, but before proving the theorem, let me show you why the theorem handles this case of k independent sets. So let's go back to what we saw before. So we got these two bounds, right? So we had, and basically this summarizes the bounds. So gamma I decays like roughly 1 over I. So the top levels are really nice, but as we get closer to 0, it sort of decays, like, you know, it becomes big. Now let's plug it back here. So now, so in the case, so this way. So again, consider the question for sampling k independent set in the regime we talked about, where k is not too big. So there we saw the bound gamma I was at most 1 over I plus 2. Right, this was the bound we saw. And now let's plug it here, and what do we get? Let's see. So what do we get? So we're trying to understand lambda 2 of, well, u k minus 1 dk. We're trying to analyze it lower walk from level k to level k minus 1 back to level k. It's most 1 minus 1 over k, product of I from 0 to k minus 2. No, I'm just going to plug it here. So what is 1 minus gamma I? It's I over I plus 2. And you see, this is exactly sort of a canceling, sort of telescopic sum. So this is going to be, so what are we going to get here? Well, the top part is going to be 1 minus 1 over k. The top part is going to be, you know, k minus 2 factorial. And the bottom part will be everything starting from 2 up to k factorial. So it's going to be k factorial. But we start at 2. We know the factor of 2 here. And overall, what do we get here? We get 1 minus, you know, some constant over k cubed. So the important thing here is that the gap from 1 is noticeable. It's an order of 1 over k cubed. So we can sample. So this gives us the following corollary. The mixing time of the MC algorithm for k independent set in the regime we talked about is what? Well, we have to pay k cubed to even, you know, after every k cubed step, lambda 2 becomes a constant. And then it depends on logarithmic in the size of the set of objects we care about. So we log, sorry, log of what? Well, how many independent sets do we have in general? Well, at most n to the k, right, over epsilon. And you see this is sort of, you know, polynomial in k and logarithmic in this is some poly k log n of 1 over epsilon, which is fast for us. So I mean, the exact parameters maybe are less important. So really what I want you to see that the fact we can handle the case of most gamma i's are small and few of them are big allowed us to extend the analysis from the case of zero local spectral expansion to the case of close to 0 local spectral expansion. And concretely, the way we did it is said, well, we can bound the top level by some direct calculation, and then use a trickling down theory and show that if you go down to the food chain, the gamma I diagonals become bigger, but not too big, not too fast. Sort of luckily, it all worked out, and you got this sort of nice bounds. So this was one of the motivations for Alev-Lau to prove the theorem. So what I want to do now, so maybe now remaining time, is to prove to you the theorem. But before that, let me see if anybody has any questions on the theorem, on the notations, or what do we.
I'm sorry. So we had gamma I as at most 1 over I plus 2, right?
Yeah. Mm-hmm.
And then we said take product of 1 minus gamma I.
Yeah.
So I'm wondering if it should be I plus 1 divided by I plus 2.
Yes, I think so.
Oh yeah, you're right. Mine, sorry. That's.
Yeah, I think you're supposed to get a better bound.
Yeah. So so somehow I made a mistake here, saying, oh, it should be this. You're right. My bad. You're right. This should be a minus 1 factorial. This should be k squared. You're right. This is k squared. My mistake. Is this okay now?
I think so. Yeah.
Yes. Good catch. Thanks.
Yeah, I think this is right now. Yeah.
Yeah, you're right. Okay. Thanks. Nice. Any more questions? Okay. So now let's prove the theorem. So this is what we're trying to prove. So we're saying that, well, we have some bound on gamma I for each level, and we want to combine them together to get a bound on the, basically, on this expander as a random walk expander, you know, how fast the lower walk mixes. And okay, so now we're gonna, so maybe now remaining time, we want to prove Alev-Lau theorem. So I just want to do a quick recap about notation. So this is just a recall or recap. So a matrix M is PSD, positive semi-definite, if there are two equivalent conditions, where one is that for every F, MFF is at least 0, or if equivalently all the eigenvalues M are non-negative. So this was one definition we saw last time. And we also discussed this notion of PSD order, where we said that a matrix M1 is, so it's this curly greater than M2 if M1 minus M2 is PSD. So this was this PSD order we discussed last time. And what we saw last time, so the crucial step in the proof for zero local spectral expanders were the following. So we showed that MK plus, so the lower walk at level K, then the non-lazy upper walk at level K is smaller or equal in this sort of PSD order than UK minus 1 dk. So this was, again, what do we have here? The in this PSD order, the non-lazy upper walk is of smaller than the lower walk. So this was in the case of zero local spectral expanders. And in general, we will show the following bound when it's not a zero, but something more general, where MK plus is smaller or equal than 1 minus gamma K minus 1 U K minus 1 dk plus gamma K identity, gamma K minus 1 identity. So the general result of the proof said, well, take the maximal lambda 2 of a fixed at level K minus 1, this is gamma K minus 1, so we can bound the non-lazy upper walk at level K by a convex combination of two things. One is the lower walk at level K, and the other one is just identity. Notice the identity is always a trivial bound because what we have is a stochastic process. So all the eigenvalues are always between 0 and 1, or at most 1 at least. Could be negative, but at most 1. So if we just the bound of I, that's a trivial bound for every stochastic process. But we'll say that the only tiny fraction of I there. The rest comes from a lower walk, and somehow that's going to be crucial for us in proving the theorem. So the proof is going to have two steps. So step 1, let's call this star. So step 1 will be to prove star. And step 2 is going to be to use star to prove what we want. So maybe let's just do it in order. So first thing, we're going to prove star, and then the next step is going to use star to sort of prove theorem. So everybody's happy so far? Any questions on what we're trying to do? I mean, at this point, it should not be clear maybe why star is going to give us the bound that we want, but we already saw that white was useful when gamma was 0. It was useful then, so it shouldn't be too surprising. It's going to be useful now. Only question is what bound is this going to give us? Okay. So let's start by proving that. So what did we do last time? So last time, and by last time I mean when we analyzed the case of zero local spectral expanders. So what we said is, well, how can we use MK plus? Well, we're going to use Garland's method. So last time, so we used Garland's methods. or one of the versions of Garland's method. And we said, well, so we're trying to prove this. So we're going to look at the difference and try to understand its eigenvalues. So we're going to look on mk plus minus uk minus 1 dk ff. So this is what we're trying to analyze. This is what we did last time. And this is still what we're going to do now. So we're going to difference between the non-lazy upper walk and the lower walk at level k. And our goal is to prove this is not, before it was, looking at this is different, so this should be negative or non-positive at least. Now it's going to be slightly different. So what did we say last time? Well, we could always just write this, as two components, so it's going to be mk plus ff minus uk minus 1 dk ff. And again, now we're going to use Garland's method and restrictions to move from analyzing functions f. So here f is some function on the k level of the complex. And we want to use restrictions to move to a function on the first level of k minus 1 links. Right, so this is going to be by Garland's method, just the expectation over tau in, tau coming from pi k minus 1, so the distribution on level k minus 1 of just the difference of the two things. So it was, just to remind you, it was a tau, f tau minus the expectation of f tau squared. So this is, we're just applying Garland's method that we saw already several times. So we just move. So now f on tau is, a function on the first level of the link of tau. And now we just deal with, an a tau is the adjacency matrix of the graph, or the normalized one, underline the link tau. And what did we do before? So before, and this is we're going to diverge. So before, we just bounded it by saying, well, this is at most, well, this is going to be, before all the eigenvalues were 0 or negative. So before we could just say, well, this is smaller than, So then just this, before this was just, this is at most 0. And the reason was that, well, all the eigenvalues were non-positive, and this difference is exactly, so you take the top, you take the normalized adjacency matrix A tau, you say, well, it has a top eigenvalue, f tau, we remove it by minus expectation squared, with all the other ones are negative. Now we cannot do this anymore, so we have to be a bit more careful in what we do. So what do we do? Well, we do what we always do. We're going to decompose the function on the link to the parallel part and the orthogonal part. Right, so we're gonna be more careful. So first step is we're gonna decompose f tau into the parallel part and the orthogonal part, like we've seen several times already. So the parallel part is just, some constant, the average of f times the one function, and the orthogonal part is, whatever you have left. And now we can just say, well, what are we going to get here? Well, this is going to be exactly, well, what is a tau, f tau? F tau is going to be, before I do that. So what is now a tau? These restrictions, well, it's exactly going to be a tau. The parallel part plus the orthogonal part, right? So these parts of act differently or orthogonally on a tau. so they don't mix with each other. And what is this first part? This first part is, well, what is f parallel tau? It's just average of f, or f on the link times 1. So this is just going to be equal to the average of f on the link squared. Right, again, we're just looking link by link. So we have a graph, we have a constant function on the nodes. We apply this random walk on this constant function, with again a constant function. So the inner product is just the average of the function square, which exactly, cancels, the average function here. So what we get here, so what we have left here is just the action of a, and I don't know why I have, it should be denoted this a. So what we have left here is just the action of A on the orthogonal parts. Before we said, well, this is going to be at most 0, because all the eigenvalues are going to be at most 0. Well, now we can't say it anymore, but now we're just going to apply the bound that we know on the eigenvalues, which is gamma k minus 1, because tau is a k minus 1 phase. So now we can say instead, so now we can bound this by at most gamma k minus 1 f tau perpendicular. Okay, so we're just applying the bound again. We're trying to get a one-sided bound. Gamma k minus 1 is a maximum over all lambda 2 over all faces in level k minus 1. Take the worst one and apply it here. So overall, when we put this together, what do we get? So overall, what did we get here? We got it mk plus minus uk minus 1 dk ff is smaller than the average over tau from k minus 1 faces of well, gamma k minus 1 f restricted to tau perpendicular f restricted to tau perpendicular. So that's a bound that you get by just applying the eigenvalue assumption on faces in link k minus 1. Okay, so now let's continue from here. We want to keep simplifying it. So I'm going to say this is just write equivalently as well. I'm going to move the gamma part out, just a constant average tau by k minus 1. And I'm going to express a orthogonal part by the difference from the function and the function from the parallel part. It's going to be f tau minus f tau parallel, f tau minus f tau parallel, right? So that's what the perpendicular part is. And again, if you do the inner product, they don't mix. So you get this going to be equal to gamma k minus 1, same expectation, tau, and pi k minus 1 of what is going to be f tau minus the parallel part. And now we can again apply Garland's method and then go back from k minus 1 links to the full function. So that's going to be equal to gamma k minus 1 ff minus uk minus 1 dk ff. So I'm again applying Garland's method to go back to something that's global on the function and not local in links. So first we apply Garland's method to move from the global function to links. We did the analysis of the links. We use the bound on the lambda 2 to simplify the expression to get a bound, and then we moved back. So overall, what did we find here? So we have this expression we're trying to find here. mk plus minus uk minus 1 dk ff is smaller than gamma k minus 1 ff minus again uk minus 1 dk f. So you see, this is the same expression here and here.
Shachar, maybe I'm missing something. Something seems weird here.
Okay.
That somehow you've when you separate the parallel parts, you have two negatives. Why are you still getting minus?
Because you have two negatives and one positive, right? So the inner product of f tau and f parallel tau is f parallel tau.
Oh yeah, right.
So it's like invariant, right? You have x minus expectation of x.
Yeah.
Two
Okay.
negatives and positive.
All right. Yeah.
So I'm claiming that now, once we've achieved that, then just if you just reorganize, you get the expression you want. So reorganizing it. So reorganizing gives what we want. So it gives that mk plus f is smaller than 1 minus gamma k minus 1 uk minus 1 dk ff plus gamma k minus 1 ff, which is what we're trying to prove, because this is almost identity ff. Right? This is exactly what we're trying to prove. So this is just reorganized the terms here. So again, even if there's not tons of intuition here, so really what they did here is sort of going from global functions to link functions, applying the bound on lambda to there, and then rolling back. And sort of it works. So I mean, if it's not clear to verify it, like here on the fly, just read it in the notes later. It's slowly verify it for yourself that all the calculations work. I unfortunately don't have much more intuition than that, like why this specific thing works, but it just works. So now, so this finished part one. Like, how do we derive this star expression? And then the next step is how do we use this to prove a theorem? But maybe before doing that, let me see if anybody had any questions how we derived star.
I mean, really make a parallel to something we saw in the expander case here. So I still think kind of, okay, this doesn't really tell you why it works, I guess, but again, this is the same sort of structure where we kind of know how to apply expansion on graphs, right? And so we break things down onto graphs and apply the expansion. And a place where we've kind of seen something similar to this is when we talked about the mixing. Like on your homework, you improved kind of the hitting set result to be non-trivial. And one way to do this was to analyze the Rayleigh quotient and to break things into perpendicular and parallel parts. And this is kind of exactly what we've done here from the zero local spectral version, where we still kind of, the only difference really is that we've added the step where you kind of first decompose over links, and then you do a similar type of analysis, where in the version we did in class of kind of this hitting set version, there was no 1 minus gamma on the first term. And then when you did the better analysis, when you broke it into the perpendicular and parallel part, you got this 1 minus gamma, and that ended up giving you a non-trivial bound for kind of all values of gamma. And it's the same thing here. So this is very similar to when we did the hitting set analysis and the improved hitting set analysis. So this zero local spectral expansion versus gamma local spectral expansion is very similar.
That's right. By the way, I'm thinking here that so what they did here is really sort of give this more refined one of saying, let's assume the maximum in each level. You could hope to say, well, maybe in some cases you need an even more refined one where you do like in a link by link type of analysis. And yeah, I don't know, I'm guessing probably people are going to come up with even more refined analysis for some specific applications. And I have no clue what they're going to be, but probably something. I mean, because the things are not so symmetric, right? It could be that a few of them are bad, but many are good, and maybe that's going to be good. I don't know. I'm thinking out loud. I'm not sure.
Yeah, it'd be difficult because right now we bound things by pulling out the maximum, right? And so I think it's difficult to apply Garland's method if you're separately bounding each link.
No, I agree the same proof won't work. You get probably a different bound. But it's like, for example, if you take like the Lovász-Loka lemma, right? So initially the bound there will fill up this uniform case, and then people impose the non-uniform case by a more refined analysis. So I'm guessing here you could probably do something similar, but I guess maybe a fair thing is to find like an application where this would be useful, and then figure out what would actually be needed. That would be my guess. Okay, so moving forward, let's see how we use this. So, okay, so what did we, so far, solving two. So we showed that, MK plus is smaller than this PSD order from 1 minus gamma K minus 1 UK minus 1 dk plus gamma K times identity. And our goal now is to prove the following bound: the mixing time of the lower walk. Our goal is to prove that the lambda 2 of u k minus 1 dk, so the lower walk at level k, is at most 1 minus 1 over k, product of I from 0 to k minus 2, 1 minus gamma I. And we're going to do it by induction. So we're going to do it by induction on k. Okay, that's going to be one thing. And the other thing we're going to do is we're going to use the fact that, well, lambda 2 of uk minus 1 dk, so the lower walk is going to be the same as, lambda 2 of, just flipping the order. So they lay the upper walk at level k minus 1. Right? But if we take two operators and we flip them, it doesn't change the sort of spectrum. It might add zeros or remove zeros, but the spectrum doesn't change. It's just so that. So here, what we're saying is this is going to be, this is sort of the, this is the lower walk, level k. This is a lazy upper walk at level k minus 1. So what we care about is at level k, but we can sort of flip and go to a different walk, the upper walk on level k minus 1. It's going to simplify the walk for us. So just to see, so what happens if k is 1? So if k is 1, the bound we're trying to prove here is 1. So it's 0, right? And what do we have here? So what is lambda 2 of, d1 u0? So we start at level 0, which has single node. We go up to level 1, we go down. So just a single eigenvalue there. It's going to be 1, and from there on, everything is going to be 0. Just because, this is a walk from a space with like a one-dimensional space. It has like one eigenvalue, and the rest by definition is going to be 0. So that's what this is trivial. This doesn't use any property of the complex. So we're only going to start, so having to use the complex from k being 2 and above. So let's do that. So let's look on as a proxy mk minus 1 plus ff. So what we want to do is we want to analyze, okay, maybe before doing that. So we want to analyze, so we want to bound now, lambda 2 of dk uk minus 1, and we're going to do the Rayleigh quotient. So let's fix f in ck minus 1. And our goal will be to analyze, to bound this sort of dk uk minus 1 ff, but as a proxy, we're going to use mk minus 1 plus the non-lazy walk. So first of all, before bounding it, we're just going to remember that by definition, it's a mixture of what we care about, which is going to be dk uk minus 1 ff and the identity operator. I'll just move stuff around here a bit. So it's going to be this. So let's just write the expression here. So it's going to be k over k minus 1 okay, so this is just another way of saying that, if we take the lazy upper walk at level k minus 1, it's a mixed combination of the non-lazy walk mk minus 1 plus, and the lazy part staying at f. This is just a flip it. So we've seen it several times already. So this is sort of, remember, this is what we're trying to bound. So this is what we care about. So we just express this as a combination of, you know, ff and, you know, the lazy part. And also, let me also assume here, just for so it's easier to write things down, so that let me also assume here that we have this f and ck minus plus. We care about lambda 2. So we want to assume that f is orthogonal to 1. So the Rayleigh quotient with respect to f would characterize lambda 2. And also for convenience, let me assume that the norm of f is 1. So we don't have to keep carrying the norm of f everywhere. Okay, so this ff here is just sort of 1. Okay, so now we're going to use the bound that we have on mk minus 1 plus. So now using star, so this is using star, we can bound this as what? As 1 minus gamma k minus 2 u k minus 2 d k minus 1 ff plus gamma k minus 2 ff. Right, this is what we just proved, that we can, this mk minus 1 plus in the PSD order, well, we put for mk plus, but we applied now here for mk minus 1 plus. It's smaller in the PSD order than a combination of the lower walk at the appropriate level, in this case, k minus 1, and the identity operator. Again, ff here is going to be 1. So now we're just going to apply, now we can just use induction to apply the bound that we want for here, right? This is exactly the expression we have in an induction case. So we can now just apply induction and say, well, this is going to be what? That's going to be smaller than 1 minus gamma k minus 2. And now by induction, 1 minus 1 over k minus 1, put it level k minus 1, product of I going from 0 to k minus 3, 1 minus gamma I plus gamma k minus 2. And already setting that f in the product f is 1. So this is a bound we have by induction. And now we just need to make sure everything here works, right? And so just sort of simplify it and write this as follows. That's going to be, I'm claiming that's going to be exactly as 1 minus 1 over k minus 1, product I from 0 to k minus 2, 1 minus gamma I. Let's also verify that. So we almost got the expression that we wanted. Now we just have to sort of shift things around a bit and sort of finish the proof. So I'm just going to basically take this expression and sort of isolate it. So this is what we care about. So the mixing of the upper level walk level k minus 1. So it's going to be smaller than what? Well, then when it's going to be k over k minus 1. Because it's multiplied by, sorry, other way around. K minus 1 over k. So this is what it's multiplied for by times 1 minus 1 over k minus 1 product of I from 0 to k minus 2, 1 minus gamma I, plus again adding this ff. So it's going to give me again plus 1 over k. And again, you just can put them all together and say this is just equal to, you know, 1 over k. Sorry. Just equals to 1 minus 1 over k product I from 0 to k minus 2, 1 minus gamma I. That's it. So I mean, so we got this bound, but I mean, to me, the most interesting part is saying, well, once we got this sort of way of connecting the non-lazy upper walk to the lower walk, this will give us some bounds using induction. And here we're just working out the details and seeing what bound this gives us. right? So this is just a calculation. It's probably best if you verify it for yourself, no, on your own time. There's not a lot of intuition in it other than this is a bound you get by applying induction. But we saw that this bound is useful, right? If the gamma i's, most of them are really close to 0, and a few of them are big, then it's useful for us. So this sort of finishes this part. And really you can ask, well, what can you do next? And the point here is that, well, we have the theorem, which is great. It's really useful. It's been used in all over the place. How do you bound these gamma i's? So the real question here so what do we want? So we want to bound these gamma i's, right? The maximal, to remind you, this is the maximum lambda 2x tau, tau in xi. And we saw one way of doing it. So one way is where we first we sort of bound gamma like d minus 2 somehow, you know, by hand, and then we apply the trickle down theorem, right? Sort of we get some bound, really good bound for the top level. We trickle it down. Hopefully, you know, it trickles all the way down, and we're happy. But not this. This only works. This only works if, you know, when we go to the down, we get a non-trivial bound. This only works if gamma d minus 2 is at most 1 over d. It doesn't work if it's more than that. You get a trivial bound for like the 0 complex, and you cannot apply this at all. Right? Even if like one of the gammas equal 1, this will give you a trivial bound of 1. You get nothing. So it works really well if the top one is really, really good, and then you go down, it becomes worse and worse, but not too bad. But turns out many other examples where actually what you get is out of the opposite behavior. The top levels are bad expanders, but as you go down in the complex, you get better and better expansion. And this is like a very different phenomenon that we see from the trickle-down theorem. So what I want to show you on Thursday is some aspect of that called spectral independence, which is a technique that was invented to basically prove exactly this type of behavior. So what we're going to see is that if the objects we're trying to study have a certain nice correlation pattern, and I'll explain this, you know, in detail on Thursday, then you can actually prove that the top level is bad, but as you go down, it becomes better and better. So you get this flipped behavior, but you can still apply Alev-Lau. And to me, really, it showed that we don't really know what's going on here. I mean, we don't know what are the right bounds here. When we have two different theorems that give like opposite behavior, probably none of them is the truth. Probably there's something that we don't understand yet, which is why this is an exciting area, right? It's like a very active area. All of these results here for the last couple of years. And people keep discovering new things. And my guess is that, no, if we teach this again 5 years from now, we're going to teach completely differently, because people are going to discover new things, and then we're going to simplify and unify many of the results here. On the other hand, if you want to do research here, it's a great time, because we understand something, but we know that many things we don't understand well enough yet. So this seems to be like a great time to start or enter research in this area, whether if you care about combinatorics, or you care about sampling, or you care about all of the other things that we didn't cover in this class, but that are related here, like topology or algebra or many of the other applications. Yeah. So let's see if anybody has any questions, and if not, then this will be the end of today, and then we'll finish on Thursday with spectral independence.
It might be worth mentioning, although Shachar, I imagine on Thursday, maybe you'll go into this a little bit, but kind of what's going on with this, and you kind of briefly mentioned where we've bounded for kind of k less than some, when we were looking at fixed size independent sets, we had this bound on k that we needed. And one way to look at this is like, well, you need some bound on K just to be able to find an initial independent set to start the sampling, which is reasonable. But there's also this this area called statistical physics that a lot of the stuff we're going to see is kind of coming from, where you have these kind of parameter regimes and something called phase transitions, where when K is kind of above some value, it turns out that you can prove like a computational hardness result. Like unless kind of NP equals RP, this problem is hard to sample. There's kind of no efficient sampling algorithm. But as soon as K is less than this threshold, there are polynomial time approximation schemes. And a lot of what happens here and the kind of the breakthroughs that HGX have brought have actually been to show these exact thresholds where we kind of knew hardness up to some place, but we couldn't quite prove sampling up to it. And HGX has actually allowed us to kind of get this whole phase transition worked out, where we know past some parameter regime up to some reasonable computational assumption, like P equals NP or NP equals RP or something like that, we know hardness. And then up to that exact value, we know kind of a polynomial time approximation scheme, which is pretty cool. And this somehow, I don't quite understand the physics very well because I'm not a physicist, but this somehow actually corresponds to something very physical, some kind of behavior of like gas spin systems and that behave very similarly, where kind of past some threshold, you get very different physical behavior in a system of particles. And then kind of things are hard on the complexity side of things. And then you get kind of better behavior before the threshold. And there's this whole area of kind of these interesting connections between physics and computational hardness that HGX have had these huge breakthroughs in, which is pretty cool.
Yeah, definitely.
Do you have like the papers that correspond to like those HGX results in statistics in physics?
Like the exact connections between physics and
no, like the papers that you were just referring, or like the results that you do, like do they have, like, are you referencing a paper in particular, or?
Well, it's like a whole street. I mean, this whole area is like, so like, for instance, we're going to talk next time, Shahar will talk about what are called spin systems, which is, and like the Ising model. So the Ising model was initially to model like simple systems in physics, right? And then it became kind of big in machine learning and computer science. And so the next thing, the spectral independence that we're going to cover, was actually used to prove mixing bounds on Ising models. And like, yeah, I mean, the papers that Shahar will be talking about are exactly this. I mean, they should be in the notes, but
yeah, I think in the notes we list some of them. We don't list all of them, and also in a month there will be more papers.
Yeah, if you look in the last section, in the last section of 8, so the one that we'll teach on Thursday, there should be a bunch of references to. There are just tons of these papers. They keep coming out like constantly. These like spin system mixing bounds, because they have like awesome connections to these other areas, and they're like very natural problems in CS that we're getting these kind of polynomial time and statistical threshold behavior for.
Right.
Yeah, they should be in the notes.
Okay. Yeah. Thank you.
Yeah, and I mean, since one lecture left. Sorry, what?
What?
No, go ahead. What?
I was just saying, I don't know how much intuition for the physics stuff you'll get from reading the CS paper. I get the feeling that the CS people maybe don't in general really know what's going on in the physics side of things. That's kind of the physicists seem to know. So I definitely don't know much about that.
No, but the connections are actually not that complicated. So what is statistical physics in general? So you want to model this big system, let's say billions or trillions of gas particles or something, and you want to understand the macro behavior of the system, right? Not each particle where it's moving, like in classical physics, but you want to understand the global behavior, like like maybe the pressure or the temperature, or if you have like a magnetic system, do you have all the particles pointing in the same direction, like in a magnet, or like randomly looking like in a non-magnetic material? So the way this is modeled in physics is by short interactions, right? If particles are really close to each other, then they sort of affect each other. Let's say the magnets, they have some forces. If they're far, we're just going to disregard it. So you can model this with something called a graphical model, right? So you have these particles, and the graph of the nearby one that of modeling interactions. And the way you say it, well, every possible, let's say, configuration, let's say you have like a system where particles can point up or down, like in a magnet, and it has some energy associated with it. Like if they're pointing in the same direction, there's some penalty. Opposite direction, maybe it's positive or the other way around. And you want to understand, what should be the energy levels. Like if this system has to be, so if you take the system in some temperature and you let it sort of, evolve naturally, what configuration is it going to evolve into, or what distribution? And this is exactly this type of, spin systems that we're talking about. So really, so imagine you have, like a coloring of a graph, and you say, well, two nodes that are, adjacent by an edge should not have the same color. Well, that's what's called the hardcore model. This is how we don't allow things. You could say, well, if they have the same color, you can penalize it. And this will be much closer to the physical system. So in this sense, what's called the combinatorial, the hardcore model is sort of like a limit of physics, basically when you take the temperature down to 0. And I think you can sort of try to tweak this temperature and see how the system behaves. And the systems have phase transition. So at some sort of temperature that we have in one way, suddenly you change, you become a different system. And like, for example, like superconductors, they have exactly this way. It's like a system that if you move below a certain threshold because of quantum behavior, suddenly your resistance becomes not negligible, but actually 0. So people have different models for the things. And in physics, they observe that there's this phase transitions in different regime of parameters that corresponds to the solution structure. And what people in CS are doing is saying, well, this is actually very much connected to the complexity of computational problems connected to systems, whether it's sampling solutions, counting solutions, approximating things, whatever. And people are trying to understand the connection. And it seems like there is some connection between regimes where it's hard to estimate physical properties to regimes with computational complexity hardness, and the other way around. It's not a one-to-one thing, but there's some connections. And this has been sort of studied for the last probably 40 years now. And people keep discovering new things. And what HDX allowed people to do is say, in these easy regimes, where it seems from the physics side that the system should be simple, we didn't know how to analyze the algorithms. The algorithms were there. They were very simple. They worked in practice. We just didn't know how to prove that they work always. And now HDX allowed you a new tool to prove that they work all the way to the regime where they're supposed to work. By sort of empirical physical results. So this is a connection. Yeah, so it's really cool connections. But also I think some of the questions that people come up with in CS are different than the physics questions. They're not always just trying to model the physical system, but they're trying to ask different questions. Like, can you learn a system? Can you complete a system? You do very thing that might be less natural from a physics viewpoint, but might be more natural, from like a CS viewpoint.
Complete the system?
Well, I can't hear you.
Did you say complete the system?
Yeah, imagine something like the Netflix puzzle, right? Where you have some system and some of the particles, the configuration, you want to sort of figure out the rest. So, maybe for a magnetic system, this doesn't make much sense, but for like the Netflix puzzle, it does make sense. So it depends on but you can model things in a similar setup, even though from the physics viewpoint, some of them model physical systems and some of them do not. Yeah. Anyways, now seems like a good time to stop for today. So I guess we'll see you all on Thursday. Bye, everybody.